Hello and welcome to our presentation on microhydro based at Cotehele Mill in southwest Cornwall, presented by Design 143 Group 13 with Jack Ayland, Connor Banks, Kate Martin and William Fox.
Using various literatures, the calculated power output of the potential site is 18.1 kilowatts, which is the direct harness of power available for electricity production. Based upon cumulative research from respective experts in the field of microhydro, the best turbine choice is crossflow or Banke-Mitchell, with an efficiency of approximately 80% for river flow between time exceedance 0.3 to 0.8 probability.
Using a variety of resources, an in-depth analysis of impulse reaction and gravity turbines was undertaken. This information was tabulated to create the decision matrix as shown, rated from 5 as excellent to 1 as poor. A cross-flow turbine proved to be the most applicable due to its high scores and suitability from the head flow graph on the previous slide. Alternative designs included the Archimedes screw, which was not suitable for the flow data. A Francis turbine was a good contender, however it came out as more expensive.
As a result, return on investment after calculation comes to £14,000, considering annual maintenance costs as projected by British Hydropower Association. In connection to the forecast installation costs, the predicted BHA costs suggest an expenditure of £147,000, resulting in a payback period of 10.5 years. An expected turbine lifespan of 50 years will provide a net total profit of over £557,000 to the National Trust.
A mind map was created to visually display factors to consider and explore throughout this project. The 3 circles hold the main internal factors, and surrounding shows the external factors. The overlapping between circles indicates areas in which 2 sectors will dictate the outcome. For example, when choosing the type of building materials for the power plant, the aesthetics and cost will together dictate the outcome. The external factors to the right-hand side are people and company-based, of which liaisons will occur. To the left-hand side, technicalities are displayed, such as suitable IP ratings and abstraction license. A series of consultations will be undertaken at various stages of this project to gauge, inform, discuss and welcome suggestions with various parties. To name a few, the National Rivers Authority, wildlife and conservation agencies, the District Council and local residents. A prototype survey shown on the slide has been created to get feedback from local residents on any potential issues that the project may create and suggestions.
The specification includes many important factors which have been derived from various parties, including the National Trust, Environmental Agency, and feedback from local residents amongst visitors of Cotehele. Important considerations are the safety, periodic design, and simplistic design relating to overall cost and the return of investment period.
The most important wildlife consideration is the migratory salmonid classification of fish. Crucially, their ability to flow upstream against turbulent flows caused by the hydropower tail race and surge of water entering the weir. As shown in the previous video, fish screens and filters can be employed to reduce the danger of wildlife entering the turbine system. The Environment Agency Act of 1995 is primarily designed to ensure regulations are met regarding fish passes, correct screening, and the general design of the turbine water flow characteristics throughout all stages of microhydro development. This will include frequent communications between affected parties like the National Trust, building contractors, and planning partners. As shown here, various designs of bypass systems incorporate the forebay tank and tail race, which redirect fish and any debris through a humane bypass to avoid any detrimental impact upon the fast revolving turbine runner. This forebay tank design illustrates a potential bypass system for the fish, along with a hydraulically operated 2-way sluice gate to control the direction of water between the turbine and 18th century millhouse, incorporating the original wooden leat and flume. The site is based in Cotehele Woods, which has a high tree density amongst numerous walkways for National Trust visitors close to the turbine location.
An actuator operating a runner, along with a rotating butterfly valve, demonstrates two conventional methods of regulating the kilowatt output via the control gear, here using a cross-flow turbine for demonstration purposes.
To preserve the original leat, but prevent humans and falling debris from trees interfering with the mechanics of the hydropower station, some utilities could be added. A galvanized mezzanine floor with a coarse grating would ensure humans remain guarded from any sluice gate mechanism. In addition, an integrated leaf and contingency mesh to avoid any blockage could be incorporated on the side of the mezzanine floor to prevent debris blocking various pipes. A more elaborate self-sufficient system might include an automated leaf extraction conveyor system with dumping gutter to remove excessive debris during, say, the autumn period. Likewise, access points like manhole covers would help speed up routine maintenance. Other considerations include the incorporation of the original rack and pinion wooden sluice gate on the mill house and the consideration of leat and penstock cross-section shape to increase efficiency.
The National Trust flour mill is an 18th century building that is designed using Yenadon quarry stone. There are a few considerations that have to be thought about to design the powerhouse. The considerations include recreational users and agencies who would be directly affected by the location of the powerhouse, while also thinking about what materials will be used to build the powerhouse. To give a visual representation of the sort of challenges the transportation of the materials and building equipment will have, this video shows the pathways which are the two access pathways for plant equipment, considering the road width, weight restriction, wall obstructions and overhead power lines. Access to the site is limited by a variety of factors such as a 7.5 ton weight restriction and 8-foot vehicle width limit down the public highway. The site itself can then only be accessed through an old arable marshland with a 1 ton weight restriction, meaning materials used must be transported slowly and very carefully. Electricity generated from the powerhouse will be supplied to the grid, which will be installed by the contractor Western Power Distribution. To set up the grid connection, certain regulations need to be complied with and safety precautions need to be put in place, such as a way to avoid danger from overhead electrical lines. Upon correspondence, various literatures have been obtained from Western Power Distribution detailing electrical paths and construction guidance.
This slide displays many of the design considerations that have been taken into account so far. For example, the power plant will make use of oak beams and slates in keeping with local buildings. An older turbine design can be created externally for historical value, which may add value for National Trust visitors. The slide also shows considerations for the way in which water will be directed between sites and the overflow.
This aerial view represents the conventional layout we wish to employ for our micro hydro setup. The actual design of the powerhouse is composed of 3 different parts. These are the powerhouse building itself, the equipment pad, and a concrete pad. With these in mind, the building can be split into further sections. The concrete pad, which is below the equipment pad to support it, should be strong enough to hold the equipment, while the equipment pad is in place to mount the equipment. The powerhouse should be orientated so there is a straight penstock going into the powerhouse. This layout design specification will be incorporated into the final design.
A long-term saving through the reduction of operation labour includes the installation of control gear with manual commands, i.e. buttons, and visual indicators like flashing lights and wavering dials. The panel will include input-output command wires and 3-phase 240-volt distribution cables for the generator to the transformer. Electrical protection is mandatory to ensure the safe and smooth transfer of electrical power between the generator and step-up transformer. Achieved using rectifiers, overload protection, which commonly includes MCBs, isolators and essential earthing wiring, the control panel must also accommodate a program logic control setup which utilizes input signals from various forms of input and analog devices to regulate the kilowatts and associated turbine speed outputs. Input devices may include resolvers, proximity sensors and relay timers, and mechanical outputs may include linear actuators for turbine runner adjustments, motors via inverters for the shut-off valve hydraulic oil transfer pump and for the hydraulic two-way sluice gate, including the leaf extractor conveyor. Electrical outputs may include a flood shutdown system and changeover relay switchgear to transfer surplus energy to the grid via the step-up transformer. Some of the pros to our design include the minimalistic powerhouse design, a fish-friendly structure, and a maintenance-friendly design.
The cons are expensive control system and limited access to the tail race.
During the Design 143 project, Group 13 have worked in an efficient manner to achieve realistic goals, as well as the propensity to work to one's strengths. Learning outcomes include the improved ability to carry out meticulous research, record data accurately, appreciate the substantial factors of hydropower, and build upon activities like video editing, CAD animation, and hand illustrations.